Welcome to Cosmic Whispers, where cosmic mysteries come alive. Your journey beyond the stars begins now. In 1924, a young Soviet biochemist named Alexander Oparin published a slim volume that would fundamentally alter humanity's understanding of life's origins. His book, The Origin of Life, proposed something revolutionary. Life didn't require divine intervention or mysterious vital forces. It could emerge naturally from simple chemical processes operating over vast timescales. Oparin's central insight was deceptively simple, yet profound. He envisioned Earth's early atmosphere as a reducing environment, rich in methane, ammonia, hydrogen, and water vapor, but critically lacking free oxygen. In this primordial soup, he theorized, organic molecules could form spontaneously through chemical reactions powered by lightning, ultraviolet radiation, and volcanic activity. These molecules would gradually increase in complexity, eventually giving rise to the first primitive life forms. The scientific establishment initially greeted Oparin's hypothesis with skepticism. The prevailing view held that organic compounds could only be produced by living organisms, a concept known as vitalism. Every great journey starts with a few brave explorers. Right now, Cosmic Whispers is just beginning, and your support means everything. If you enjoy unraveling the mysteries of the universe, hit subscribe. It's free and it helps us grow this community together. Oparin's theory gained credibility in 1953 when Stanley Miller and Harold Urey conducted their famous experiment at the University of Chicago. They recreated Oparin's proposed early Earth conditions in a sealed apparatus, circulating methane, ammonia, hydrogen, and water vapor past electrical sparks simulating lightning. Within days, their sterile system produced amino acids, the building blocks of proteins, and life itself. The Miller-Urey experiment represented the first successful laboratory demonstration that life's fundamental components could arise from purely chemical processes. The results sent shockwaves through the scientific community and validated Oparin's theoretical framework. However, questions remained about the exact composition of Earth's early atmosphere and whether the laboratory conditions truly reflected ancient environmental realities. Throughout the 1950s and 60s, researchers refined and expanded upon Oparin's original concept. They discovered that organic molecules could form under various atmospheric compositions and energy sources. Experiments using different gas mixtures, ultraviolet light, and even shock waves from simulated meteor impacts all produced complex organic compounds. These studies revealed that the chemical pathway to life might be more robust and inevitable than previously imagined. Oparin's work established the foundation for what would eventually become astrobiology, the scientific study of life in the universe. His hypothesis suggested that if life could emerge naturally on Earth through chemical evolution, similar processes might operate on other worlds with suitable conditions. This possibility transformed the search for extraterrestrial life from science fiction speculation into legitimate scientific inquiry. The implications extended far beyond Earth's origins. If organic molecules formed readily under early planetary conditions, then the raw materials for life might be abundant throughout the cosmos. Astronomical observations would later confirm this prediction, revealing organic compounds in meteorites, comets, and even interstellar space. Oparin's chemical genesis theory provided the theoretical framework for understanding how life might arise wherever suitable conditions exist. As the 1960s dawned, space exploration programs began, incorporating biological objectives into their missions. The success of Oparin's hypothesis and the Miller-Urey experiment convinced scientists that life detection should be a priority for planetary exploration. This marked the beginning of humanity's systematic search for life beyond Earth, a quest that continues to drive space exploration today. Oparin's revolutionary vision transformed our understanding of life from a unique terrestrial phenomenon to a potentially universal process governed by chemistry and physics, setting the stage for the modern search for life in the cosmos. The 1960s marked a pivotal transition from theoretical speculation about extraterrestrial life to active scientific investigation. Oparin's chemical evolution framework provided the conceptual foundation, But space exploration offered the first opportunity to test these ideas beyond Earth's boundaries. This decade witnessed the birth of astrobiology as a distinct scientific discipline, combining expertise from biology, chemistry, geology, and astronomy. NASA's formation in 1958 brought unprecedented resources and focus to space exploration, including the systematic search for life. Early robotic missions to the Moon and Venus revealed harsh, apparently lifeless environments. But these discoveries only intensified interest in Mars, which appeared more Earth-like with its polar ice caps, seasonal changes, and 24-hour day cycle. The 1970s brought the most ambitious life detection mission ever attempted, the Viking program. Twin spacecraft launched in 1975, each carrying an orbiter and lander equipped with sophisticated biological experiments. The Viking landers touched down on Mars in 1976, initiating humanity's first direct search for extraterrestrial life on another planet's surface. Viking's biological experiments were ingeniously designed to detect metabolic processes that would indicate living microorganisms in Martian soil. The labeled release experiment added radioactive nutrients to soil samples, monitoring for radioactive gas production that would signal biological consumption. The pyrolytic release experiment attempted to detect carbon fixation, a process fundamental to photosynthesis and chemosynthesis. The gas exchange experiment searched for metabolic gases that microorganisms might produce or consume. The results proved tantalizingly ambiguous. The labeled release experiment initially produced positive signals, releasing radioactive carbon dioxide when nutrients were added to Martian soil. However, control experiments suggested chemical rather than biological explanations. The lack of organic compounds detected by Viking's gas chromatograph mass spectrometer further complicated interpretation, leading most scientists to conclude that chemical processes, not life, explained the results. Despite Viking's inconclusive biological findings, the mission revolutionized astrobiology by demonstrating the feasibility of remote life detection and revealing Mars's complex chemistry. The results highlighted the challenges of distinguishing biological from chemical processes and the need for multiple complementary detection methods. Simultaneously, terrestrial research was expanding the known limits of life through extremophile studies. Scientists discovered microorganisms thriving in environments previously considered uninhabitable: boiling hot springs, highly acidic waters, extreme salinity, intense radiation, and crushing pressure. These discoveries, pioneered by researchers like Thomas Brock at Yellowstone National Park, revealed that life could survive in conditions far more extreme than previously imagined. The study of extremophiles fundamentally altered astrobiology's perspective on habitability. If life could flourish in Earth's most hostile environments, then potentially habitable zones around other stars might be much broader than originally conceived. Subsurface oceans on icy moons, previously dismissed as too cold for life, suddenly became compelling targets for astrobiological investigation. Theoretical advances complemented experimental discoveries during this period. Scientists developed increasingly sophisticated models of planetary atmospheres, surface chemistry, and the conditions necessary for life's emergence and persistence. Computer simulations began exploring how different atmospheric compositions might support or inhibit biological processes under varying stellar radiation regimes. The 1980s saw the establishment of the NASA Astrobiology Institute and similar programs worldwide, formalizing astrobiology as a legitimate scientific discipline. These institutions brought together researchers from diverse fields, fostering interdisciplinary collaboration essential for tackling astrobiology's complex questions. By the decade's end, astrobiology had evolved from Oparin's theoretical framework into a comprehensive scientific program, combining laboratory experiments, space missions, and theoretical modeling. The field had established key principles. Life might be more resilient and widespread than previously thought. Multiple detection methods were necessary for definitive identification, and the search required systematic exploration of diverse environments both on Earth and throughout the solar system. This foundation prepared astrobiology for the next revolutionary phase, the discovery of planets orbiting other stars and the expansion of life's search to truly cosmic scales. The 1990s initiated an unprecedented transformation in humanity's understanding of planetary systems and the potential for life beyond our solar system. Until this decade, the only known planets were those orbiting our Sun, making it impossible to determine whether Earth-like worlds were common or extraordinarily rare throughout the universe. This changed dramatically in 1995 when Swiss astronomers Michel Mayor and Didier Queloz announced the discovery of 51 Eridani b, the first confirmed exoplanet orbiting a Sun-like star. Their detection method, radial velocity measurement, monitored the subtle gravitational wobble that orbiting planets induce in their host stars. The discovery shocked the astronomical community. 51 Eridani b was a hot Jupiter, a gas giant orbiting extremely close to its star, completing an orbit in just 4 days. This unexpected finding challenged existing theories of planetary formation and migration. If gas giants could exist in scorching orbits where rocky planets were expected, then planetary systems might exhibit far greater diversity than our solar system suggested. The discovery launched what astronomers dubbed the exoplanet gold rush, as researchers worldwide developed increasingly sensitive detection methods. The transit method emerged as another powerful technique for exoplanet discovery. When planets pass in front of their host stars as viewed from Earth, they cause minute but measurable dimming. This method not only confirmed planetary existence, but also provided crucial information about planetary size, orbital period, and atmospheric composition through spectroscopic analysis of starlight filtered through planetary atmospheres. Ground-based surveys, like the Hungarian Automated Telescope Network, began systematically monitoring thousands of stars for transit signals. These efforts culminated in space-based missions designed specifically for exoplanet detection, most notably the Kepler Space Telescope launched in 2009. Kepler revolutionized exoplanet science through unprecedented precision and duration of observations. The mission monitored over 150,000 stars simultaneously for 4 years, detecting minute brightness variations indicating planetary transits. Kepler's discoveries transformed our understanding of planetary demographics throughout the galaxy. The mission's results were staggering. Kepler detected over 2,700 confirmed exoplanets and identified thousands of additional candidates awaiting verification. More importantly, statistical analysis of Kepler data revealed that planets are ubiquitous. Nearly every star in our galaxy likely hosts at least one planet, implying hundreds of billions of worlds in the Milky Way alone. Kepler's discoveries introduced the concept of the habitable zone, the orbital distance range where liquid water could exist on a planet's surface. This zone depends on stellar temperature and luminosity, being closer to cooler stars and farther from hotter ones. Planets orbiting within this zone became prime targets for detailed atmospheric studies and life detection efforts. The mission identified numerous potentially habitable worlds, including Kepler 452b, dubbed Earth's cousin for its similar size and orbital position within its star's habitable zone. Kepler 438b became another celebrated discovery. A planet just 12% larger than Earth, orbiting a star remarkably similar to our Sun. Statistical analysis of Kepler data suggested that approximately 20% of Sun-like stars host Earth-sized planets within their habitable zones. This extrapolates to potentially 40 billion Earth-like worlds in our galaxy alone, providing an enormous population for astrobiological investigation. Transit observations also enabled atmospheric characterization through transmission spectroscopy. When exoplanets transit their host stars, stellar light passes through their atmospheres, creating absorption features that reveal atmospheric composition. Early studies detected water vapor, methane, and carbon dioxide in hot Jupiter atmospheres, demonstrating the feasibility of detecting potentially biological signatures in smaller, cooler planets. The exoplanet revolution fundamentally transformed astrobiology's scope and ambition. Rather than focusing solely on Mars and solar system moons, researchers could now contemplate life detection on worlds orbiting distant stars. This expansion required developing new theoretical frameworks for understanding how different stellar environments might affect planetary habitability and biological evolution. Ground-based extremely large telescopes, including the 30-meter telescope and European Extremely Large Telescope, began construction with exoplanet atmospheric characterization as primary objectives. These facilities would provide the resolution and sensitivity necessary for detailed spectroscopic analysis of potentially habitable worlds. The exoplanet revolution established that Earth-like planets are common throughout the galaxy, providing countless opportunities for life to emerge and evolve under diverse conditions. The 2010s and 2020s have ushered in an unprecedented era of sophisticated life detection capabilities, combining cutting-edge space telescopes, advanced analytical techniques, and artificial intelligence to systematically search for biosignatures across the cosmos. This modern phase builds upon decades of theoretical groundwork and technological development to bring humanity closer than ever to answering the fundamental question of whether life exists beyond Earth. The James Webb Space Telescope, launched in 2021, represents the pinnacle of current exoplanet atmospheric analysis capabilities. With its 6.5-meter segmented mirror and suite of infrared instruments, JWST can detect and analyze atmospheric compositions of exoplanets with unprecedented precision. The telescope's spectroscopic capabilities enable identification of water vapor, carbon dioxide, methane, and other molecules that might indicate biological processes. JWST's early exoplanet observations have already yielded remarkable discoveries. The telescope detected water vapor in the atmosphere of WASP 96b, a hot gas giant, and provided detailed atmospheric profiles of several rocky exoplanets. Most significantly, JWST has begun analyzing potentially habitable worlds within stellar habitable zones, searching for the chemical signatures that might indicate living processes. The Transiting Exoplanet Survey Satellite, or TESS, launched in 2018, continues Kepler's legacy of systematic exoplanet discovery with enhanced capabilities. TESS monitors the entire sky, observing 200,000 of the brightest nearby stars for planetary transits. This all-sky survey approach identifies planets around stars close enough for detailed follow-up studies, with JWST and ground-based telescopes. TESS discoveries have revolutionized understanding of planetary system architecture and habitability. The mission has identified numerous potentially habitable worlds, including TOI 700b, an Earth-sized planet orbiting within its star's habitable zone. These discoveries provide prime targets for atmospheric characterization and biosignature searches. Modern biosignature detection strategies have evolved far beyond simple searches for water or organic molecules. Scientists now focus on atmospheric gas equilibrium, chemical combinations that would rapidly disappear without continuous replenishment by biological processes. The simultaneous presence of oxygen and methane, for example, would strongly suggest biological activity, since these gases react chemically and would vanish within geological timescales without biological production. However, identifying true biosignatures requires careful consideration of false positives, non-biological processes that might mimic biological signatures. Photochemical reactions, volcanic outgassing, and stellar radiation effects can all produce chemical signatures resembling those expected from life. Researchers have developed sophisticated atmospheric models to distinguish biological from geological or photochemical processes. Ground-based, extremely large telescopes currently under construction will complement space-based observations with unprecedented resolution and sensitivity. The European Extremely Large Telescope, with its 39-meter primary mirror, will be capable of directly imaging potentially habitable exoplanets and analyzing their atmospheric compositions. The 30-meter telescope and Giant Magellan Telescope will provide similar capabilities, creating a global network of advanced observatories dedicated to exoplanet characterization. Artificial intelligence and machine learning have become indispensable. tools for processing the vast datasets generated by modern astronomical surveys. Algorithms can identify subtle planetary transit signals in telescope data, classify stellar variability patterns, and even predict which stars are most likely to host habitable planets. Machine learning techniques have already discovered numerous exoplanets missed by traditional analysis methods. Current candidate worlds under intensive study include Proxima Centauri b, the nearest potentially habitable exoplanet located just 4.2 light-years away. This world orbits within its red dwarf star's habitable zone and represents humanity's best near-term target for detailed atmospheric analysis and potential biosignature detection. TRAPPIST-1 system, containing 7 Earth-sized planets with at least 3 in the habitable zone, provides another compelling target for comparative planetology and habitability studies. The integration of multiple detection methods, transit, photometry, radial velocity measurements, direct imaging, and atmospheric spectroscopy creates a comprehensive approach to exoplanet characterization. This multi-technique strategy reduces false positive risks and provides robust confirmation of planetary properties and potential habitability. Modern astrobiology has evolved from Oparin's theoretical framework into a data-rich, technology-driven science capable of systematically surveying thousands of potentially habitable worlds. The current generation of instruments and methods has brought humanity to the threshold of potentially detecting life beyond our solar system, fulfilling the scientific vision that began nearly a century ago, with Oparin's revolutionary insights about life's chemical origins. The next 2 decades promise to revolutionize humanity's search for life through an unprecedented convergence of advanced technologies, ambitious space missions, and revolutionary analytical techniques, building upon nearly a century of progress. Since Oparin's foundational insights, the future of astrobiology will combine direct exploration of potentially habitable worlds within our solar system with increasingly sophisticated detection of biosignatures around distant stars. Europa Clipper, scheduled for launch in 2024, represents the most ambitious mission yet designed to explore a potentially habitable world beyond Earth. This spacecraft will conduct multiple flybys of Jupiter's ice-covered moon Europa, using radar to probe beneath its frozen surface and confirm the existence of a subsurface ocean. The mission's sophisticated instruments will analyze Europa's thin atmosphere and surface composition, searching for chemical signatures that might indicate biological processes in the hidden ocean below. Europa's subsurface ocean contains more water than all Earth's oceans combined, maintained in liquid form by tidal heating from Jupiter's massive gravitational field. If life exists in this alien environment, it would represent a completely independent genesis of biology, fundamentally altering our understanding of life's universality and the conditions necessary for its emergence. The Dragonfly mission, targeting Saturn's moon Titan for a 2034 arrival, will deploy a rotorcraft to explore this methane-rich world's surface and atmosphere. Titan's thick atmosphere and lakes of liquid hydrocarbons create conditions unlike anywhere else in the solar system, potentially supporting exotic forms of life based on entirely different chemistry than Earth's water-based biology. Mars Sample Return, a joint NASA-European Space Agency mission planned for the late 2020s, will retrieve carefully selected rock and soil samples from Mars for detailed analysis in Earth's most advanced laboratories. These samples may contain preserved biosignatures from Mars's warmer, wetter past, potentially providing definitive evidence for ancient Martian life. The search for technosignatures, evidence of technological civilizations, has gained renewed scientific legitimacy through projects like Breakthrough Listen. This program systematically monitors nearby stars for artificial radio signals, optical pulses, and other indicators of advanced technology. Unlike previous searches, Breakthrough Listen employs machine learning algorithms to identify patterns that might indicate non-natural origins while filtering out terrestrial interference. Artificial intelligence applications in astrobiology extend far beyond signal processing. Advanced algorithms can now predict which exoplanets are most likely to be habitable based on their orbital characteristics, stellar properties, and atmospheric compositions inferred from transit observations. Machine learning systems analyze vast databases of spectra to identify subtle chemical signatures that human researchers might overlook. The next generation of ground-based telescopes will enable direct imaging of potentially habitable exoplanets, a capability that will transform biosignature detection. The European Extremely Large Telescope's 39-meter mirror will collect sufficient light to analyze the atmospheric compositions of Earth-sized planets orbiting nearby stars. These observations will search for simultaneous detection of oxygen, water vapor, and other molecules that together would strongly suggest biological activity. Space-based interferometry missions under development will achieve even greater sensitivity for exoplanet characterization. These missions will combine light from multiple spacecraft to create virtual telescopes with unprecedented resolution capable of detecting and analyzing potentially habitable worlds around stars hundreds of light-years away. The philosophical implications of discovering life beyond Earth cannot be overstated. Even finding simple microorganisms on Mars or Europa would demonstrate that life can emerge independently under different conditions, suggesting that biology might be a common feature of planetary evolution throughout the universe. Detecting biosignatures on distant exoplanets would extend this conclusion to galactic scales. The discovery of technological civilizations would raise even more profound questions about intelligence, consciousness, and humanity's place in a populated universe. Such a discovery would necessitate entirely new fields of study, including xenolinguistics for communication attempts and xenosociology for understanding alien societies. Contemporary astrobiology research increasingly focuses on developing frameworks for recognizing life that might operate according to completely different principles than Earth's biology. This includes theoretical studies of silicon-based chemistry, ammonia-based biochemistry, and even more exotic possibilities like plasma-based self-organization or quantum-coherent biological processes. The continuing legacy of Oparin's vision extends beyond the specific search for life to encompass a broader understanding of complexity, self-organization, and the emergence of order from chaos. Modern astrobiology integrates insights from systems, biology, complexity theory, and information science to develop comprehensive theories of how lifelike processes might emerge and evolve under diverse conditions. As we stand on the threshold of potentially answering one of humanity's most profound questions, the search for life continues to drive technological innovation, international cooperation, and scientific discovery. From Oparin's revolutionary chemical genesis theory to today's sophisticated biosignature detection programs, this quest represents humanity's most ambitious scientific endeavor, one that may ultimately reveal we are not alone in the cosmos.